Willie, are you ready? Okay. Well, let's go ahead and get started then. And I am very, very privileged to introduce not just a colleague and friend in the earlier session, but a friend in this session as well, in the person of Russ Howell. Russell Howell is professor of mathematics and holder of the Kathleen Smith Chair of Natural and Behavioral Science at Westmont College, where he's been for most of his teaching career. He's had stints along the way at Calvin College, the University of Maryland, at Oxford University. He has degrees in computer science from the University of Edinburgh, mathematics from Ohio State University. His research area is in complex analysis, and he recently received an NSF grant to pursue curriculum reform in that subject at the undergraduate level. He was twice honored with Westmont's Teacher of the Year Award, and takes delight in helping students see connections between their faith and academic pursuits. He was the first coordinator of Westmont's Faith and Learning Program for faculty members. He's published in standard mathematics journals, but also in sources usually targeted to the humanities, such as Novum Testamentum, Eerdmans, and InterVarsity Press. An article of his was selected as one of 25 to appear in the 40th anniversary edition of Christian Scholars Review. Russ enjoys tennis, playing the piano, hiking with his wife Kay, and his yellow lab Dickens. He's an active member of the Free Methodist Church of Santa Barbara. Just before Russ comes to speak to us, I just want to let you know that tomorrow he will be speaking at 3:30 in D52, and this will be what Dr. Lunsford referred to as the math talk. That is, it's going to be for mathematics faculty and for students, but it's open to the public. So if you're prepared for the math talk, then 3:30 in D52. And at 7 p.m., he'll be speaking in Harvey Hall, and there he'll be giving a faith and mathematics talk, and so also open to the public. You're welcome to join us there. I had the privilege of getting to know Russ when we were both recipients with about 33 other folks of a Templeton grant that brought us to Oxford University for 3 summers in a row to think about faith and science. And we spent our mornings in seminars, and then the afternoons for Russ it was playing tennis and other fun things, and working on various writing projects. During one of his stints in Oxford, he's been there more than once, during one of his stints in Oxford, he co-authored with James Bradley, Mathematics Through the Eyes of Faith. And I recommend this book to you. My wife and I were actually reading it to one another on our way to and from Champaign, Illinois this weekend, and it was a lot of fun, not just because we knew the author, but because of his ability to communicate. Russ will be speaking to us this evening on the Lewis-Anscombe debate, Milieu, Mutations, and Mathematics. So join me in welcoming Russell Howell.
Good evening. It's a pleasure to be here. I didn't know ahead of time that there would be people a distance away, so greetings to you in Germantown, was it, and Hendersonville. It's, as I said, a pleasure to be here. Just a quick plug about the 7 o'clock title tomorrow. The title of the lecture is a 2-part question. Number 1, is faith required for mathematics? And number 2, is mathematics required for faith? So welcome to any of you that want to come to that one. As Ben said, the talk in the afternoon is more highly mathematical than that one will be. I sort of feel a little bit a mathematician speaking on C.S. Lewis in an audience that's no doubt filled with philosophical and literary scholars. Feel a little bit like the bind that the Chauffeur was put in by Einstein. When Einstein was to deliver a lecture and had a sore throat and said to his chauffeur, I can't do this hour lecture, you're going to have to do it for me. And the chauffeur said, what are you talking about? I'm not a physicist. Come on, you've heard my lecture millions of times. I know you've got it memorized. I heard you saying it the other day as we were driving. So he twists his arm, and the chauffeur agrees to give the lecture. Einstein says, it takes 1 hour, and there won't be any time for questions, so just do it. Well, the chauffeur was a bit nervous and talked fast and got through the lecture in 50 minutes. So the host at that point said, well, are there any questions for Dr. Einstein? And someone asked a very highly technical question. But with a flash of insight, the chauffeur said, that question is really easy to answer. In fact, my chauffeur can answer it himself. And so during the question and answer time, if there are any questions that I can't answer, I'm going to defer them to my chauffeur. Now, those of you that are in Hendersonville or Germantown may not recognize this person. It's Justin Barnard, who has organized this series, and I was disappointed to find out that I can't defer to him because he's not here. So I'm going to defer to my host instead. Now, you heard from Dr. Lunsford that he might be hearing a little bit more about miracles. And the Lewis-Anscombe debate grew out of Lewis's book that he actually published in 1945. He wrote a letter to his aunt saying, I'm done with the miracles book, but it didn't hit the press until 1947. And in 1948, on February 2nd, he had a discussion, actually some call it a debate, with the philosopher Lewis-Anscombe. In Chapter 3 of Miracles, Lewis made an argument for the incoherence of naturalism. Of course, the purpose of writing miracles in the first place was to paint a philosophical picture that would make miracles compatible. And such a view is incompatible for a naturalist. A naturalist is someone who doesn't believe there are any supreme beings, that nature is a closed system, and hence there are no miracles. And Lewis's argument was to show that on a naturalistic view, our ability to reason is inconsistent. It's an incoherent position. Now, Anscombe was a staunch Catholic, and so she certainly was not a naturalist. She just thought that Lewis's argument for the incoherence of naturalism wasn't compelling. Now, there's various spin-offs about how the debate went, and many people think that Anscombe got the better of Lewis during that debate. In fact, some people say he was so shattered that he gave up writing Christian apologetics altogether. When I was in Oxford, I had a discussion with Michael Dummett. He is a philosopher of mathematics and was actually at the Lewis-Anscombe debate. I had tea with him one day, and so put the question to him directly. What do you think? Is it true that Anscombe got the better of Lewis? Absolutely. She trounced him. That was his comment. Now, whatever the true situation was, it certainly seems to me not the case that Lewis gave up his hope in Christian apologetics, because he rewrote the chapter. He rewrote that for the second edition of Miracles that was published in 1980. And if he had lost all confidence, I don't think he would have even bothered to rewrite the chapter. So I'd like to take a look at the differences between the two editions of the book. In the 1947 edition, you see that the title of Chapter 3 is The Self-Contradiction of the Naturalist. In 1960, he nuanced that a bit. Rather than making it a contradiction, he just called it The Cardinal Difficulty of Naturalism. And that suggests that he was taking Anscombe's criticism seriously and modifying his argument. There are other comparisons and similarities that you can make. Both editions have the header quotation from the literary critic Ivar Richards. We cannot have it both ways, and no sneers at the limitation of logic amend our dilemma. You'll see what that means by having it both ways in a minute. Both introduce a key criterion that should be used when assessing a worldview. It follows, says Lewis, that no account of the universe can be true unless that account leaves it possible for our thinking to be a real insight. So if you give an account of the universe that doesn't allow for thinking to be a real insight, then you can't trust the validity of that account of the universe. And you're winding up in sort of a morass, according to Lewis. The additions are similar there, but then they differ in the example Lewis chooses to argue his main point. In the first edition, he gives two reasons why a man may think that a dog is dangerous. The first is from observation. The dog is muzzled. Messengers always try to avoid going to the house in which the dog resides. The second reason is irrational, according to Lewis. It's from a phobia. The man sees that the dog is black, and he happens to have been bitten by a black dog when he was a child, and so he thinks the dog is dangerous. That's where Anscombe hit Lewis. She said, there are causes, you're saying causes are just rational or irrational. There could be non-rational causes that wouldn't have to be irrational. And so the 1960 edition of the book distinguishes two ways that we use the word because. Lewis dubs the first one cause-effect. A person states that his grandfather is sick because the grandfather ate bad food the previous day. That's a cause-effect response. The second Lewis calls ground consequent. A person states that his grandfather must be sick because grandfather is still in bed. He knows that grandfather always rises early unless he is ill, and so that person has made an inference, ground consequent. The 1947 edition gives comparatively little elaboration on the rational-irrational distinction. By contrast, Lewis spends quite a few pages unpacking more what the grandfather illustration means. Finally, the concluding paragraph of 1947 is a rather harsh treatment of an argument that Lewis says some naturalists make. By contrast, the 1960 version ends with a summative conclusion of Lewis's earlier remarks. Overall, the strategy for both is a little bit different. Naturalism is incoherent in the first edition versus, well, maybe it's not incoherent, but theism is the best view, the better view of the two. I'm going to return to Lewis after a bit, but only after introducing you to an article written by the Nobel laureate in physics, Eugene Wigner, someone who lived in completely different worlds from Lewis. He was a nuclear physicist, and he wrote an article about mathematics, published again the same year that Lewis wrote the second edition of Miracles. The article that Wigner published dealt with a miraculous phenomenon of a sort. Wigner's intention was to raise an interesting aspect about mathematics that, as far as the article went, had nothing whatsoever to do with naturalism. But on closer inspection, you'll see that it does, and you'll also see, I hope, that spin-offs from the ideas of Wigner and those of Lewis are inextricably linked. Wigner's article bears the title, The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And he starts with a story about two friends who are discussing their jobs. One of them is a statistician and is working on population trends. He mentioned a paper he had written that contained a complicated-looking equation on the first page. You see it right there. The statistician attempted to explain the meaning of it, as well as the other mathematical symbols in the paper. His friend wasn't trained in mathematics and so was a bit overwhelmed. He kept saying, "How do you know that?" And finally, "What is this symbol here?" "Oh," said the statistician, "that's pi." "What's that?" "The ratio of the circumference of the circle to the diameter." "Well, now you're pushing the joke too far. Surely the population has nothing to do with the circumference of the circle." Wigner uses that story to introduce two questions. Number one, how is it that scientists have used mathematics so often to build successful theories relating to the physical world? And number two, we might call this a nagging Kuhnian-like question. How can we be sure that completely different theories would not be as successful as the ones we now use, though perhaps concentrating on different phenomena? Regarding Wigner's first point, he concedes that much of mathematics, such as Euclidean geometry, was developed because its axioms were created on the basis of what appeared to be true of reality. For example, Euclid's very first axiom says you can draw a line between any 2 points. Sure, that just seems to be the way things work. From this viewpoint, the applicability of mathematics to the physical world is hardly surprising. But much of mathematics doesn't progress in that matter. A good argument, in fact, can be made that other factors guide the formation of a large body of mathematical theories. Dr. Mitchell mentioned that my area is complex analysis, so let's take that as just one example. It grew up mathematically in the mid-1500s. And at that time, the notion of complex numbers, which involved the square root of -1, you might remember, that notion, the square root of -1, that seems strange. Negative numbers themselves were still being treated with suspicion by the mathematical community at that time. After all, there was no physical reality corresponding to something negative. So taking the square root of a negative number was even more problematic. But mathematicians kept using their imagination and pressed forward. They developed logical theories to accommodate these numbers, but the process took time, in fact, about 300 years. It wasn't until the end of the 1800s that the subject became fully embodied in the corpus of mathematical literature. Now, for our purposes, here's the important point. No physical phenomenon at all guided the formation of the theory of complex numbers, none whatsoever. Progress came from abstraction and the manipulation of mathematical symbols in accordance with specified rules of algebra. But now, complex numbers play a pivotal role in helping physicists understand the quantum world. And for Wigner, the early use of quantum mechanics led to a miracle, in the same kind of sense that Lewis uses the word miracle, we'll see. It arose when Max Born, Werner Heisenberg, and Pascual Jordan decided to use mathematical constructs known as matrices to represent the position and momentum variables in equations involving classical mechanics. Later, Wolfgang Pauli successfully applied this technique to the mechanics of the hydrogen atom. Wigner states that this success was not surprising because the matrix procedure was abstracted from problems dealing with the hydrogen atom in the first place. But then, matrix techniques were applied to the helium atom. There was no justification for this move because the calculation rules were meaningless in that context. Yet the application worked remarkably well. According to Wigner, the miracle occurred when the calculation of the lowest energy level of helium agreed with the experimental data within the accuracy of the observations, which is 1 part in 10 million. Surely, says Wigner, in this case, we got something out of the equations that we didn't put in. Wigner cites other examples. Newton's law of motion, formulated in terms that appear simple to mathematicians, but which proved to be accurate beyond all reasonable expectations. Quantum electrodynamics and the pure mathematical theory of the Lamb shift. The thrust of Wigner's main point in all of this can be illustrated by comments he makes near the beginning and end of his paper. Early on, he says this: the enormous usefulness of mathematics in the natural sciences is something bordering on the mysterious, and there is no rational explanation for it. In concluding his paper, he says, the miracle of the appropriateness of the language of mathematics for the formulation of the laws of physics is a wonderful gift, which we neither understand nor deserve. We should be grateful for it and hope it will remain valid in future research, and that it will extend, for better or worse, to our pleasure, even though perhaps to our bafflement, in wide branches of learning. Wigner uses the word miracle 12 times throughout his paper. In some instances, he probably intends it to mean nothing more than phenomenally surprising. But in other places, he seems to be pushing for something deeper than that. Now, what exactly is a miracle? Lewis defined it in his book Miracles as some kind of interference with nature by a supernatural agent. And he described a naturalist as someone who thinks nothing exists except nature. So, as we said earlier, for a naturalist, there are no supernatural powers and no miracles. Now, admittedly, the meaning of nature needs clarification, and Lewis spent some time doing that in his book. And the term interference a miracle as an interference of nature, is a bit problematic for Christians who believe that the laws of nature are general descriptions of God's continued sustenance over his creation. So how is that an interference? Now, Lewis was aware of those difficulties, but going into that kind of nuanced elaboration was beyond the scope of his book, I think, and likewise, these definitions will suffice for our purposes. Curiously, there was no response to Wigner's paper for 20 years. But finally, in 1980, the computer scientist Richard Wesley Hamming took up the task. Like Wigner, Hamming was impressed with the success of mathematical theories. He himself had used these theories in developing an algorithm that is now known as the Hamming code. It is used to correct and detect errors when data are transmitted from one computer to another. So whenever you go on the internet, the Hamming code is at work. Hamming's goal was to tackle the unreasonable effectiveness question implied by the title of Wigner's paper, and he offered 4 partial explanations that could account for the applicability of mathematics. You see the first one right there. First, scientists see what they look for, and so they craft postulates so that they will produce theories that conform to their prior observations. Because scientists look at the world through a mathematical lens, it's not so surprising, is it, that they describe it in mathematical terms. Second, scientists select the kind of mathematics to use. The same kind of mathematical theory doesn't work everywhere. Different theories are selected in accordance with the phenomena they seem to describe. Now, those two observations are kind of similar, and each is reminiscent in some sense of Wigner's Kuhnian-like question. How do you know these theories are the ones that should work? Maybe other theories would do just as good a job. Maybe it's just effort that you're doing here to explain things. So regarding the selection of mathematics to fit our perception of reality, we've already acknowledged that some of mathematics develops that way, but not all of mathematical theories that are applicable are generated out of a concern for applicability. So further work must be done, and Hamming gives 2 additional answers to serve as food for thought. The third one is not very satisfying. It's that science actually answers comparatively few problems. To the extent that this assertion is true, the less of a miracle the success of mathematics would be. And Hamming says biology, for example, has not yet been successfully dissected by the mathematical scalpel. Since Hamming has written that, the field of mathematical biology has exploded. But regardless of what you think about that, the main problem is the success of mathematics and physics. And how do you account for that? And Hamming's fourth answer provides an obvious and plausible mechanism for doing that. It's evolutionary accounts. Evolution provides an explanation of why humans are to mathematize the physical universe. That might seem plausible at first, but it's not fleshed out by Hamming at all beyond this comment. Darwinian evolution would naturally select for survival those competing forms of life which had the best models of reality in their minds. Best for surviving and propagating. That's what best means. It's interesting that Hamming concludes with the following remark. If you recall that modern science is only about 400 years old, and there have been from 3 to 5 generations per century, then there have been at most 20 generations since Newton and Galileo. If you pick 4,000 years for the age of science, generally, then you get an upper bound of 400 generations, or 200 generations, sorry. Considering the effects of evolution we are looking for via selection of small chance variations, it does not seem to me, says Hamming, that evolution can explain more than a small portion of the unreasonable effectiveness of mathematics. I don't find that explanation very compelling. Just as an inclined block on an inclined plane needs a certain amount of incline before it starts sliding, but once the sliding proceeds, it progresses rather rapidly. So too one must say that, well, yeah, once science started, it took off, but any evolutionary developments that occurred prior to that time of science starting were critical, and you can't discount it. But evolutionary accounts have problems as well. And in any case, Wigner was acknowledging the possibility of such explanations in his paper. Wigner was after something deeper, hinted by his remark that he and other scientists create theories that appeal to our aesthetic sense. Before turning to spin-offs of Wigner's thinking along these lines, spin-offs that connect with Lewis and pose problems for naturalism, let's look briefly at some evolutionary models a bit, because they tie in with Lewis's account in Miracles. And specifically, I'll just look at 3 theories that have been put forth as viable evolutionary accounts of human cognition. Their proponents don't necessarily intend that their argument should apply to mathematical cognition, so any criticisms against these theories have to be taken with the requisite grain of thought. The first explanation can be called the sexual selection hypothesis, as argued by Geoffrey Miller. He claims that excessive capacities or acquisitions of resources of any kind may be a sexual display. If one has the energy or time or intrinsic capacity to do things that don't have a direct adaptive value, carrying around a big set of antlers that are so big they're more of a detriment than a defense, or walking around with a big colored tail that a peacock has, or possessing artistic or mathematical brains that are more than needed to solve the problems of survival, then that energy or time or intrinsic capacity by itself may attract mates and hence promote survival of the species. Okay, well, physical attributes certainly seem to have some role in mate attraction, and artistic brains may as well, insofar as they enable people to make attractive artifacts for display. But the argument for mathematical brains doesn't seem to hold up as well. Although Miller doesn't specifically address, as I said, the issue of mathematical thinking, there has been speculation that his thinking might be relevant. Here's what he says. The healthy brain theory suggests that our brains are different from those of other apes, not because extravagantly large brains helped us to survive or raise offspring, but because such brains are simply better advertisements of how good our genes are. But how would a larger brain be evident? And why would such an advertisement be appealing? In this regard, I'm reminded of the following cartoon by Gary Larson. It depicts 2 men on a desert island competing for attention of women. The one winning the day was the one who was able to display on a chalkboard a more impressive array of mathematical equations. So these speculations, I guess, are certainly not disprovable, but according to my biological colleagues, they don't really have any good evidence in their support, at least as they might relate to mathematical thinking. The next explanation is known as the byproduct hypothesis, as exemplified by Pascal Boyer. Boyer is an atheist, but many theists think that he are sympathetic with his main approach. He argues against there being a specific module in our brains that accounts for religious cognition. And he hypothesizes that many other higher cognitive functions may not be evolutionary adaptations at all. Instead, they may be byproducts of things that are adaptive and just piggyback on the adaptiveness of those higher capacities. For Boyer, such cognition comes from many sources, which for him explains why religious claims, taken as a whole, produce so many false conclusions. Okay, on the one hand, if the piggyback model holds up, it might be possible to extend it in some way to account for cognition in general and mathematical cognition in particular. On the other hand, some work would need to be done in that regard. How many false conclusions, for example, has mathematical reasoning produced? And again, my biology friends say, well, it's just a theory. There's not any good empirical concrete evidence, at least at this time, to support it. And finally, there's the module hypothesis, as argued by Stephen Mithen. Mithen writes from the perspective of an anthropologist, and he has a tremendous amount of archaeological data on which to draw. His theory is that higher integrative cognitive processes grew out of the unification of specific evolutionary modules, such as a module for tool use or a module for interpersonal relations. And these modules for Mithun seem to coincide with spurts of brain enlargement, which are caused by a variety of factors. For example, Mithun says, in general, larger animals have larger brains simply because they have more muscles to move and coordinate. He further writes this, in summary, science, like art and religion, is a product of cognitive fluidity. It relies on psychological processes which had originally evolved in specialized cognitive domains and only emerged when these processes worked together. Now, Mithun and others who argue along those lines paint a detailed and plausible scenario. But if that scenario were to be cast in a naturalistic framework, then it is precisely here where Lewis, in writing his third chapter of Miracles, wanted to put on the brakes. His concern was actually not against any evolutionary theory, but any evolutionary theory that is set in a naturalistic framework, where all and only relevant forces are nothing more than random, blind chance events, and thus with no oversight, if you will, of any kind, no miracle, if you please, by a supernatural being. So let's now return to the second edition of Miracles and the two ways Lewis says we use the word because, as mentioned earlier, as cause-effect and as ground consequent. For Lewis, the ground consequent, the one of making an inference, is key to reasoning. They're logically connected thoughts. How are they logically connected? For Lewis, one thought can only cause another thought by way of inference if you see it. You can see that there's a connection. Lewis then thinks it's inconceivable that a raw natural selection, which operates only on those things that reward biological responses, that is cause-effect as opposed to ground consequent, can ever raise those consequences into acts of insight. Now, Lewis's views on this matter remain controversial, but many philosophers think that his analysis is, in general, on the mark. In fact, February 2nd, 1967, exactly 19 years after the Lewis-Anscombe debate, Anscombe engaged another philosopher on Lewis's argument, this also at the Oxford Socratic Club. It was John Lucas. There you see him in his 12th century farmhouse in Somerset with his wife Moray. I was able to call in on him one day while in the UK and had a nice discussion with him on various features of the debate and other things. According to those that attended that debate, Lucas got the better of Anscombe. In other words, he successfully defended Lewis's view on miracles. This person is a very, very interesting, eccentric fellow. He rides a 1927 or 28 Humber. It was built in December of 1927, which Lucas calls its birth, and went on the market in February of 1928, which he calls its christening. 70 years after that, in 1997, to celebrate its 20th birthday, Lucas poured beer in the radiator, tied balloons to the struts, and drove around town honking its horn with a sign on the front saying, "I'm 70. Much to his chagrin, 2 days later he got a note from the parson congratulating Lucas on himself having turned 70, even though at the time he was much younger. Others have defended Lewis's views. More recently, Victor Reppert expanded Lewis's views in his book called C.S. Lewis's Dangerous Idea. A colleague of mine has, last year or so, published a nice article in a philosophy journal called The Lewis-Anscombe Debate. And finally, Alvin Plantinga has generated much discussion with his argument that is similar to Lewis in a piece that appeared on the internet at first, but now is in his book Warrant and Proper Function. And he also argues along Lewis's lines that naturalism is self-defeating. But Plantinga gives a probabilistic analysis. He notes, as Lewis did, that evolution selects for survivability and reproductive proliferation. But to use Hamming's language, even if evolution favors life forms that have the best models of reality in their mind, best is still defined in terms of survivability and proliferation, not necessarily by means of cognitive reliability. But wouldn't the former imply the latter? Wouldn't survivability imply cognitive reliability? No, not according to Plantinga at least, who spends some time arguing that it's reasonable to suppose in a hypothetical world that a high degree of survivability or reproductive proliferation could be found among creatures like us, yet whose beliefs were mostly false. He gives an illustration, for example, of a person who runs away from a tiger and thus survives, but thinks the tiger is a big fuzzy toy and thinks he is running towards the tiger. So he's badly deluded, but highly survivable. And many atheists, ironically, or naturalists, argue that belief in God, though false, is nevertheless a highly survivable trait. So for Plantinga, the odds are either very low or inscrutable that our cognitive faculties are reliable, given the tenets of evolution combined with naturalism. So any naturalist, reflecting on this state of affairs, could not have confidence that her cognitive facilities were reliable, but those were the facilities that naturalism was generated from. As Darwin himself said, "With me, the horrid doubt always arises whether the convictions of a man's mind, which has been developed from the mind of lower animals, are of any value or at all trustworthy. Would one trust in the conviction of a monkey's mind, if there are any convictions in such a mind?" That from Charles Darwin. Now, Plantinga and Lewis's arguments have not convinced many naturalists. In fact, there's a whole book out called Naturalism Defeated that takes Plantinga's essay, gives various philosophical responses to Plantinga's essay and Plantinga's rejoinder to them. He doesn't really convince them. But however his or Lewis's thinking plays out on that view, at least one can see that how beautifully a theistic view, and in particular a Christian theistic view, fits into the framework that justifies the trust in our reliability of our cognitive faculties. For Christians, we were not created by blind chance, and by whatever process God did create us, he did so with the desire that we would come to know and believe in him, rendering it very likely that the cognitive processes from which Christian belief emanates are indeed reliable. You could say the same thing for any theistic view, not necessarily Christian. So now the stage is set to map out, as promised, how mathematical elegance can pose problems for the naturalist as well. Problems in ways that mirror Lewis's own thinking about what beauty is. So let's suppose that a blind chance theory of evolution could explain how we got reliable cognition, notwithstanding the arguments that Lewis, Plantinga, Reppert, and others have made against it. Let's just suppose that that finally comes out to be successful. If so, coming as it is in the naturalistic framework, that argument would still run up against the arguments of Mark Steiner, who wrote a book called The Applicability of Mathematics as a Philosophical Problem. I'm going to focus Steiner's argument more on aesthetics than he does, but strictly speaking, Steiner attempts to refute non-anthropocentrism rather than naturalism. But if Steiner is correct, the naturalist shouldn't take comfort. For any view of naturalism, Steiner muses, is ipso facto non-anthropocentric, in that it would disallow a privileged status for humans in the scope of the universe. If, as Steiner argues, the success of mathematics can be shown to put humans in some sort of a privileged position, then naturalism has some problems to sort out. Now, how does mathematics do that? Well, for Steiner, it's not so much the success of mathematics in any one area. After all, there have been many failures of mathematics. And in this respect, Steiner is sympathetic with Hamming's third point, science relatively answers very few questions, and is critical of Wigner in citing success stories for physics, That example of pi in the population ignores all the failures that mathematicians have made to predict population trends. What Steiner's talking about, though, is the success of mathematics as a grand strategy. It's a strategy that takes, for example, the raw formalisms of complex Hilbert space theory and then boldly uses them to make predictions about the quantum world, predictions that subsequently seem to be borne out via experiment. Now, how is that phenomenon anthropocentric? Well, an analogy may be helpful. Most cultures use a base 10 counting system. No one is sure why that's the case. There's no universal consensus, but generally they think we have 10 figures. So that's why we developed base 10. And the Mayas, by the way, had a base 20 counting system. And so for many, that confirms this appendage hypothesis, if we call it that, for counting. Now, what if successful theories of how the universe operates were based on multiples of 10 in a fundamental way? That would be anthropocentric to an extreme. The only reason the number 10 is special to us is because how we appear to ourselves. But suppose further, not only did the number 10 have special significance, but time and time again, other aesthetic criteria, human aesthetic criteria, played a significant role in understanding the universe. Such occurrences, when you step back and look at them from a meta level, would surely make one wonder why this privilege seems to fall on the human species. But yet this situation is precisely analogous to what mathematicians and scientists actually do when they rely on human notions of symmetry and beauty in the development of their theories. In fact, such a strategy has been long-standing and consistent. Galileo, for example, pursued this tactic even though the best empirical evidence at the time not only didn't support, but in some ways tended to disconfirm his heliocentric theory, tended to disconfirm it. He simply adopted the heliocentric view because it gave him a more satisfying view, a more symmetry view. Physicists generally admit that elegance, beauty, and symmetry hold primary sway in theory development. Look what Brian Greene says in his book, The Elegant Universe. Physicists have tended to elevate symmetry principles to a place of prominence by putting them squarely on the pedestal of explanation. G.H. Hardy, in his book, A Mathematician's Apology, argues that mathematics itself, at least what constitutes good mathematics, is driven primarily by aesthetic criteria such as economy of expression, depth, unexpectedness, inevitability, and seriousness. Qualities that also seem to be standards for good poetry. Two of those criteria, unexpectedness and inevitability, seem at odds with each other. But how can they be put together? In a beautiful mathematical theory, there's certainly the inevitable. A theorem marches towards a conclusion that's undeniable. But how can that be unexpected? And I think the answer is in the proof of the theorem itself. A beautiful proof has ideas that take the reader by surprise, almost like a series of, if you can imagine, brilliant moves in a chess match. And the surprises, when they're put in context, become stunningly beautiful. A good poem often has that same effect. The pattern of words forms a symphony of ideas that are beautiful to be sure, many surprises to be sure, but at the end, at least with some poems, seems paradoxically inevitable. It just had to come out that way. It just had to be stated that way. Now, Lewis believed that poetry could reflect God's character in creation. And in some sense, Lewis might say that our earlier use of the phrase human aesthetic criteria was a bit of a misnomer. For Lewis, our ability to judge something as beautiful is a sign of our bearing God's image, because these judgments point to an absolute beauty. Here's what Lewis says in chapter 5, this is from the Weight of Glory. The books or music in which we thought the beauty was located will betray us if we trust to them. It was not in them, it only came through them. And what came through them was longing. These things, the beauty, the memory of our own past, are good images of what we really desire. But if they are mistaken for the thing itself, they turn into dumb idols, breaking the hearts of their worshippers. For they are not the thing itself. They are only the scent of a flower we have not found, the echo of a tune we have not heard, news from a country we have never visited. There's a close connection between beauty and goodness in Lewis's thinking. And in the Book of Miracles, chapter 5, he sees the moral judgments that we make as posing further difficulties for naturalism, thereby extending his argument from reason into the realm of value theory. It's not that the moral pronouncements of naturalists are incoherent, but that on their own view, they can only be legitimately viewed as sentiments and not genuine expressions of ought. Lewis's fiction also cast God as the source and true locus of beauty. Matt mentioned the book Perelandra in his lecture, originally published with the title of Voyage to Venus. It paints a picture of a beautiful, sinless, and freshly created world. Mark Steiner, too, sees something special in our aesthetic preferences, as do many others. William James, in one of his essays, says that of two competing criteria for epistemic truth, the one that is more beautiful trumps the other. So lots of people have thought this. And Steiner's book, The Applicability of Mathematics as a Philosophical Problem, contains several examples of beautiful mathematical systems that subsequently, and we might say miraculously, wind up being used in applications to the physical world. His surveys include the use of complex analysis in fluid dynamics, relativistic field theory, thermodynamics, and quantum mechanics. Two of examples I'll just quickly look at. Schrodinger's use of the wave equation. He begins with an equation there where E stands for energy, and it's assumed to be constant. He assumes it's constant so he can eliminate it by a mathematical technique known as differentiating. When he does that and fiddles around a bit, he gets that second equation. You don't need to know what the terms mean. The important thing is that equation is then successfully used in situations where the energy is not constant. Yet it started out by assuming a situation where energy is constant. The second is Maxwell's anticipation of a physical reality. In 1871, James Clerk Maxwell made a remarkable prediction resulting from his work in electromagnetic theory. He noticed that the experimentally confirmed laws of Ampere, Coulomb, and Faraday, when you put them in a certain mathematical form, called their differential form, contradicted the law of conservation of electric charge. How are you going to resolve that contradiction? Maxwell decided to tinker with that equation, and he noticed that if he added a term to it, the resultant equation would not only be consistent with the conservation of electric charge, it would actually logically imply it. With no other warrant or experimental evidence of any kind, Maxwell then boldly predicted that this new term that he added to his equation must correspond to some physical phenomenon. Maxwell died in 1879. 9 years later, Henrik Hertz demonstrated the reality corresponding to Maxwell's term. It's electromagnetic radiation, what we use every day. Richard Carrier is a freelance writer and science historian who is an atheist who is unimpressed with this episode. He claims that what Maxwell did is entirely consistent with naturalism. So first, Carrier states that Maxwell's putting these laws into their differential form conforms to the naturalistic observation that nature works in continuous, not broken processes. Second, Carrier argues that Maxwell took a logically sound hypothetical step. If charge isn't being conserved, it must be going somewhere. And presumably that's what led Maxwell to add that new term. Carrier then states this: Maxwell rightly picked the simplest imaginable solution first, which due to human limitation is always the best place to start an investigation, and which statistically is the most likely, as simple patterns and behaviors happen far more often than complex ones. Thus, Maxwell's moves that anticipated EM radiation were therefore a natural conclusion from entirely naturalistic assumptions. But with such language, it seems to me that Carrier plays right into Steiner's hands. Picking a simple solution in accordance with human limitations is precisely analogous